Hello students, I hope all of you are doing good. In this video, we are going to discuss few problems on NMR. As the first question is, 1H NMR spectrum of organic compound recorded on 500 MHz spectrometer. It showed a quartet with the line positions at 1759, 1753, 1747 and 1741. These are the four lines for the particular quartet. And based on this data, there are the two questions. First of all, we need to identify the chemical shift and the coupling constant for this quartet. As we know, the quartet is a splitting pattern when we are getting the separation of the lines with the equidistance positions. And these four positions are already provided. That means 1759, 1753, 1747 and 1741. So either of these two lines with the subtraction, we are getting the value that is a 6 hertz. So the distance between the two lines here, it will be the same. Whether we are taking the subtraction from either of the two consecutive lines, we'll get and we'll end up with the 6 hertz. So the 6 hertz is the coupling constant for this quartet. So that out of the four options that we have, the two options that are provided other than 6 hertz will be ruled out. So in this case, the second option and the fourth option, it will be ruled out. Now the thing is we need to identify the particular chemical shift for this quartet. And for that reason, as we are seeing this quartet, it is having a central point at 1750, that is exactly in between these two values, that is 1753 and 1747. So we can easily calculate the chemical shift for this particular quartet. That means the absorbed frequency for this quartet, that is equals to the 1750, and we are recording this NMR on a 500 megahertz. So we'll divide this by 500 megahertz. That means 500 into 10 raised to 6, and overall we'll multiply with the 10 raised to 6. So these two values will get cancelled, and 1750 divided by 500, that equals to 3.5. So in this case, the answer will be the chemical shift, that will be 3.5 ppm, and the coupling constant, it will be the 6 hertz. So therefore, in this case, the correct answer is the option 1. In the second example, it is one of the important examples with respect to the understanding of integration term. And this example is guiding in understanding that if we are taking a mixture of compounds, with the help of NMR, can we calculate the molar ratios of two compounds? So we'll try to understand this. 1H NMR spectrum of a mixture of benzene and acetonitrile showed a two singlets with equal integration. This is the information that is provided as a part of question. And based on this, the question is asked, if we are having this data, then what will be the molar ratio of benzene to acetonitrile? So this is the question. So based on this question, we need to understand one part that is related to the structures of benzene and acetonitrile. By looking towards the structure of benzene and acetonitrile, we are getting the idea that is benzene is a skeleton that is having 6 equivalent hydrogens, while acetonitrile is a structure with the 3 equivalent hydrogens. And as we know, if we are taking the NMR of benzene individually, it will give a single peak. It will give a single peak. And when we'll take a NMR of acetonitrile, it will also give a single peak. But for this individual NMRs, we cannot assign integration, and that is one of the thing that students needs to understand, that if the compound is having only one type of protons, then we are not able to give integration for the particular compound. But in this case, the question is quite interesting, that we are taking an NMR of a mixture. So if we are taking an NMR of a mixture, so in this case, the integration that we are getting for the respective compounds will help us in understanding their molar ratios. So if a mixture is given, we are not having the idea about the quantity, what amount of benzene and what amount of acetonitrile we have added, that amount can be calculated if we are getting the value of integration. So in this case, the information is provided that the two integrations, they are of uh, equal heights, or that is related to the equal areas. So what kind of thing that we can relate with this data? At the area under the peak, that we call as the integration, that is directly proportional to the number of nuclei that are absorbing the frequency. So in this case, as the integration area for the benzene and the integration area for the acetonitrile is observed to be same. So based on this, what kind of information that we can gather? The molar ratio for these two compounds, as they are recorded NMR, can be calculated like this. So the formula is the molar ratio, that is a mole of A, in this case A is a benzene, and mole of B is a acetonitrile. So it can be calculated like this. Area, that is the integration of benzene, divided by number of 1H nuclei of benzene. So in this case, as we know, in this case, this is the 6 is the number. So 6 will be the number of nuclei for the benzene, and the area of acetonitrile, it will be the 1, because as we have seen earlier, since both are giving the same equal integration, so it will be 1s to 1. And the number of nuclei, 1H nuclei for acetonitrile, it will be 3. So by just doing a simple calculation, this value is comes to be equal to 3 by 6. And so we can do a simple modification, and it will come around 1s to 2. So the straightforward answer for this particular problem is the molar ratio of benzene to acetonitrile, it will be 1s to 2. So based on the integration and the number of nuclei which are absorbing, based on these two numbers, we can easily calculate the thing related to the molar ratios of two compounds. So in this case, the correct answer for this question is option number 3. That is 1s to 2 will be the molar ratio for the benzene as to acetonitrile. In third example, there are two things that can be easily understood, and this is one of the such problems that guides us in understanding what will be the effect of machine frequency on a coupling constant, and how to calculate the chemical shifts if we are changing the machine frequencies. So first of all, we'll read the question. In a 200 megahertz NMR spectrometer, a molecule shows two doublets, and these two doublets are separated by 2 ppm. The observed coupling constant is 10 hertz. So these are the all information that we are recording an NMR on a 200 megahertz. We are getting two doublets, and these two doublets are separated by 2 ppm. And the thing is the coupling constant observed for these two doublets, that equals to 10 hertz. So based on this data, the two things are asked. First thing is the separation between these two lines, between these two signals, and the coupling constant in 600 megahertz spectrometer will be. That means, suppose we'll record the NMR of this compound on a 600 megahertz machine. What will be the separation between these two signals, and what will be the coupling constant? So for that reason, we need to understand this problem by just doing this small representation. These are the two peaks, two doublets. They are separated by 2 ppm. And as we know, if we are having the two different machine frequencies, if you are recording the NMR on a 200 megahertz, 1 ppm is equal to 200 hertz, and of course the 2 ppm will equal to the double of this. Similarly, if you are recording NMR on a 600 megahertz, 1 ppm will be 600 hertz, and the 2 ppm equals to the 1200 hertz. So the simple thing is, if the difference between the two doublets, if it is a 2 ppm, then on a 200 megahertz, this value will be equal to this. So based on this, one part is getting fixed, that the difference, that the separation between the two signals, it will be equal to 1200. So out of the four options that we have with us, The options that are not matching with this, that is the option number 3 and option number 1, will be ruled out. So out of the second and fourth, we need to identify the what will be the coupling constant. And as the theory suggests, the theory of NMR suggests, if you are recording an NMR on a different machine, one thing that is not getting changed by changing the NMR frequency, and it is a coupling constant. So the question can be asked in another format also. Does the coupling constant changes with the applied magnetic field or the machine frequency? And the answer in this case, there will be no change. So the coupling constants are independent of applied magnetic field. It means it will remain unchanged. So as the data is suggesting, the coupling constant for the particular for this compound when recorded on 200 megahertz, it is a 10 hertz. So it will remain changed when we are recording an MR on a 600 megahertz. So in this case, the correct answer for this question will be option number 4. Question number 4. The organic compound that displays following data, that is 1H NMR, is recorded on a 400 megahertz and the three values are assigned. So the three values, and for that reason we need to assign the correct structure for this data. As this data is suggesting, there are three peaks, that means there are three types of protons. And as we are having the four structures, so one by one we can try to eliminate the unwanted or wrong answers. So the thing that we discuss or we try to understand the correct structures indirectly through the point that we are having the three types of protons, and we'll try to relate with these four compounds. So one by one we'll identify. So in a compound 1, as we are seeing, this is a symmetric structure. So these are HA, that is similar protons. So this will be the first set of protons. As in this case, this will be the second set of protons. As all these are the CS3, they are equivalent. So this will give third kind of protons. So in this case, we may expect there are three types of protons. And this seems to be close to our data. But again, we need to identify the other structures. So the second structure is this CS3 will have one set of protons. Again, in this case, since it is a symmetric, so this will be the second set of protons. This will be the third set of protons, and these two CS3s, again they are equivalent, so this will give a fourth set of protons. But as per our expectation, there has to be only three kind of protons, so this is getting ruled out. In compound 3, this CS2, this will give one first set of protons. As again in this case it is a symmetric paradise substituted structure, so this HA protons will be the second set of protons. In this case, the Hb protons will be the third kind of protons. This CH will be the fourth, and these two CS3s, they are identical. This will give the fifth kind of proton. So this is also not the expected answer. In the fourth compound, we are observing these three CS3s. Again, they are equivalent. So this 3CS3 will give one set of protons. And aromatic skeleton, if you are observing, this is not a symmetric. So every proton on the aromatic skeleton will be different. So this will be the second kind of proton. This will be the third. This will be the fourth kind of proton, and this will be the fifth. So in this case also we'll have five kind of protons, and therefore this will not be the expected answer. So indirectly we have ruled out the three possibilities at the second, third and fourth. This is not correct. So our expected answer has to be option 1, and it is getting fitted that these three CS3s, it will give a singlet, and this will be corresponding from 1.29 singlet, and out of the two HA and HB protons, as This will give a doublet with this. So HA protons will give doublet with the HB, and HB protons will give a doublet with the HA protons. So this data is matching with the expected matching of these three types of protons, and option 1 will be the correct answer for this question. Question number 5. First of all, I will read the question, and then step by step we'll understand what are the hidden information in the question. The structure of the compound that matches 1H NMR data given below is 1H NMR is recorded in a DMSO-D6. As you know, deuterated solvents we are using for the NMR, and the values that of different absorptions are given like this: 7.75, that gives a doublet of doublet. 7.75, it is giving a doublet of doublet with the two coupling constant, that is 8.8 hertz, and this is corresponding for one proton. Next value is 7.58. Again, it is a doublet with the coupling constant 7. It's a 2.4. It is corresponding for one proton. Third is 6.70. It is a doublet, and it is showing 8.8 hertz. It is corresponding for one proton. 6.50. It is showing a broad singlet, and it is meant for the two hydrogens. And last one, that is a 3.8. It is showing a singlet, and it is meant for the three hydrogens. So based on this data, we need to identify the fractions of the molecule, and through this we'll try to collect the information. So one by one we'll do this. So first of all, the value, that is a 7.75, it is a doublet of doublet. It's a doublet of doublet with the two coupling constant, that is 8.8 and 2.4. So this information is giving idea about the two couplings. That's a 8.8, it is suggesting it is a ortho coupling, and 2.4, it is indicating a meta coupling. So suppose we want to get into the skeleton, this will be the proton of our interest, that is the 7.75 that we are discussing. It may have the two possibilities. First thing, it may be like this. So this will have a ortho coupling with 8.8, and this will have a meta coupling with this proton, that is a 2.4. This is one of the probabilities. And second probability is it may have ortho coupling like this and meta coupling like this. So this is the skeletal probable skeletal part of the 7.75 delta proton. The next proton is 7.58. So in this case, it is indicating that this is the proton which is showing a doublet with the coupling constant, that is a 2.4. It is indicating this is having a meta coupling. So this may have skeleton like this. So this will show a meta coupling like this. The third proton, it is 6.7, and it is showing a doublet, and it is showing only ortho coupling. So this will have a skeleton like this. So this is the basic idea that we are getting from the three aromatic compounds, aromatic protons. And the next delta value is suggesting, that is at a 6.5, it is showing a broad singlet, and that is meant for the 2H. If you are looking towards all the four compounds over here, then one common point is all the structures, they are having one common functionality, that is the NH2. So we can directly get the point that these two protons with the broad singlet, it has to be meant for the NH2. So this is suggesting that the NH2 functionality can be assigned for this. And the broad singlet, maybe we can directly assigning this is for the two identical protons. So this is directly suggesting the NH2. But in this case, we are not able to identify the exact position. So the next delta value, it is also helping us to place the appropriate positions of NH2 with respect to other functional groups. The thing is 3.8 singlet 3H. This is suggesting that this 3.8, it should be CS3, but the value that is 3.8, it means it is suggesting that this CS3 has to be attached with the electronegative group. It has to be attached with the electronegative group. Okay, electronegative group like a oxygen. So this we are expecting that this may be like a OCS3, and this OCS3 generally it is around 3.3 or 3.4. So moreover also it is suggesting that it may be either in a conjugation with electron withdrawing group, or it may have a probable hydrogen bonding. So in this case the hydrogen bonding probably it will be the intramolecular hydrogen bonding. So these are the probable subparts that we are getting from this information. So based on this, we'll try to relate this with the four probable structures, and one by one we'll try to identify which of this structure is not correct, so that we'll reach to the most correct structure. So if you are looking towards this structure, all the structures that we are getting, the part that this is hydrogen, 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 and as the skeleton that we are getting with the help of coupling constant will guide us that which of the skeleton or skeletons they are matching with the aromatic part, and you will get value that the first, second, and third, first, second, and fourth, it is showing an analogous part of with this. But the structure 3, as you are seeing, that this is showing that the hydrogens they are, it is a continuously placed. And in this case, this hydrogen will show a doublet of doublet, this will also show a doublet of doublet, and this will also show a doublet of doublet. And this is not the expected probable outcome of the compound. So therefore, the third compound will get ruled out. Of course, we are relating the data with compound one by one. And the compound 4, if you are observing, one of the things that is suggesting that this CS3, it should be attached with the electronegative atom. It should be attached with the electronegative atom. But in this case, we are observing that this CS3, it is connected with the carbonyl and it will not come around 3.8. So therefore, this CS3 will not match the 3.8 value. So therefore, this probability is also ruled out. Out of the first and the second compounds, as we are seeing, this is having a very, we can say, marginal uh, counterpoints between these two compounds. And one of the things that we need to understand that if we are thinking about uh, 6.5 NH2, and of course, one of the thing related to the this CS3, it is around 3.8, and expecting that this CS3 up expecting at 3.8, then which of this structure will most likely it will accept. So based on the fact that this NH2, if you are drawing like this, then this will show a probable intramolecular hydrogen bonding. So out of this, we can easily give a more, we can say, more technically closer data that is suggesting that the compound second has to be our choice. So we'll try to understand this. So the NH2 in this case it will give a 6.5, and this will give a broad singlet. This OCS3, since this CS3 is attached with the oxygen and at the same time this oxygen is having a hydrogen bonding, so it will have a delta positive charge. So therefore we can expect this will come around a 3.8. That is one of the thing. And in this case, this proton HA, HB, and SC. So this proton we may expect that this will give a value at, yes, since this will give only a meta coupling, so this will be the 7.58. This proton, since it will couple with this meta with HA and ortho with SC, and this is giving a doublet of doublet, so this will be 7.75. And SC proton, since it is giving only a ortho coupling, This will give us 6.7 value. So suppose we want to justify these values based on coupling constant, based on the chemical shift, then this is, as I said, we need to first of all identify those structures which are not correct, that we can rule out. So I think in this case, the compound second, which is matching with most of the things related to data, and it will be assigned as the correct structure for this given information. Dear students, I hope you will find this material will be easy to understand the basic concepts of NMR, and it will guide you in getting the fundamentals of NMR, such as the chemical shift, coupling constant, and any other things that you can relate with the interpretation of NMR. Share the channel with your friends, share the content with your friends. At the same time, most importantly, just put your comments in the chat box so that more content and the variety of subjects can be discussed in coming videos. At this moment, thank you so much. Take care.